So we have seen three examples involving strings which were somewhat similar. We started with the longest common subword, then we moved to the longest common subsequence, and then finally we expanded that to the edit distance. And in all cases, the recurrences looked similar. And now let's look at a problem where the recurrence is somewhat different. So this is a problem related to matrix multiplication. So how do you multiply two matrices? Well, if you have a matrix A and a matrix B, right, and you want to multiply them and produce a new matrix, let us call it A times B, right. So now if I look at the entry in the ith row and the jth column in the new matrix, I have to take the ith row in J, the jth column in B, so the ith row in A, the jth column in B, and then multiply these element by element. So I have to take the first element here, right. So I have to run k through these, k runs through these indices from 0 to n minus 1, and I take ai0 b0j, that is my first term. So that is this times this. Then I go to the next one, I get ai1 times b1j, right. So this is this one and this one. So in this way I keep walking down this row and walking down this column. I pair up the elements, multiply them as pairs, and then add them up. So I do this plus this, and so that is this summation. So it's the summation of aik into bkj for k ranging from 0 to n minus 1. So this is how you multiply two matrices. So in order to do this, that row, the ith row here and the jth column must have the same length, right? Otherwise you can't pair them up. So if I look at the number of columns, so this is an m row n column matrix, right, and this is an n row, this is a whatever p row or q row p column matrix, right. Then the size of the number of columns here must be equal to the number of rows here, so n must be equal to q, right. So I must have the same number of columns in A and in B so that I can multiply them. And how much time does it take? Well, A times B is an m cross P matrix, right, finally, because I am going to get entries of the form I comma j, where I is a row in A and j is a column in B. So computing each entry takes order n time because we have to run through this summation. So each entry in AB takes this much time. And how many entries are there? Well, there are m times p entries, right, it has m rows and p columns, and therefore the overall cost is going to be m times p times n, which I will write as m times n times p, right. So there are m times p entries, and each takes order n time. So this is the cost of doing one matrix multiplication using the standard definition of matrix multiplication. So we are not going to try and work with, we are not trying to improve matrix multiplication itself. We are looking at a problem where we have to multiply a sequence of matrices. So supposing we have to multiply three matrices, A times B times C. Now we can only multiply two at a time. So either we can first multiply A times B and then multiply the result by C, or we can first multiply B times C and then multiply the result by A, right. So the order left to right is important, but what is not important is the sequence in which we do this pairing up. So that is what is known as associativity, right. So we know from arithmetic that 6 plus 5 plus 2, it does not matter whether I do 11 plus 2 or I do 6 plus 7, right. So whether I do the 5 plus 2 first or 6 plus 5 first, it does not matter. So that is associativity. I could either put the bracket like this, right, or I can put the bracket like this, and both will give us the same result. Assuming I can only add two numbers at a time, I can add up anyway and I will get the same answer. So matrix multiplication is associative. So the sequence in which we pair up and evaluate this long chain of matrix multiplication operations does not really matter in terms of the answer that we get, but it does matter in terms of how much time it takes. Now the how much time it takes for an individual multiplication we know. If we take an m times n matrix and multiply it by an n cross p matrix, it will take m and p, but these matrices sizes grow and shrink in the sequence, as we will see. So supposing we have these three matrices, we have this one matrix which is kind of just one row and it has 100 columns, and this has got 100 rows and one column, and this is again a single row and 100 columns, right. So this is what it means. 1 cross 100 means one row, 100 columns. 100 cross 1 means 100 rows, one column. So it's just a single row, a single column, and a single row. And now I want to multiply A times B times C. So I can do it in these two ways, as we have seen. So let's see what happens if I do the second first. So if I do A times the product B times C. So when I multiply B times C, what am I going to get? I am going to get, this is M, this is my N, and this is P. So I am going to get an M times P matrix. I am going to get a 100 by 100 matrix, right? So B, C, the product of B and C is 100 by 100. How much time does it take? It takes M times N times P. It takes 100 times 1 times 100, right? So this takes 10,000 steps, right, to compute. Now I have this 100 by 100 matrix, right, and here I have a 1 by 100 matrix. So the final answer now is going to be 1 into 100, right, A times B times C. So A times B times C is going to be 1 into 100. How much time is it going to take? Well, I had a 1 by 100 here and a 100 by 100 here, right. So it's 1 into 100 into 100, so it's again 10,000. So therefore, computing this product by first doing B times C and then doing A into that product takes 10,000 plus 10,000 steps. If I do it the other way, then things are very interesting. First of all, this matrix, which is 1 row times 1 column, is actually just going to give me 1 entry, right? This row times this column in this product gives me 1 entry. So I actually end up with a 1 by 1 matrix. And how much time does it take? It takes time to multiply 1 row into 1 column of length 100. So it just takes 100 steps, right? And now I take this 1 by 1, right, and I multiply it by this, I am going to get a 1 by 100. But how much time is this going to take? Well, each of the rings is just one trivial, 1 by 1 is just one value, right? So it's going to be one value, one row value times one column value. So I'm basically going to take another 100 steps, 1 into 1 into 100. So 1 into 100 into 1 is 100, 1 into 1 into 1 is 100. So I get 100 plus 100, 200. So therefore, by choosing a better order, A times B first and then multiply by C, rather than the worse order, A into B times C, I have made an enormous saving in terms of how much time it takes to multiply. So the multiplication, again I am trying to emphasize, the multiplication of the matrices itself, I am not doing anything clever. I am just using the basic definition of matrix multiplication. I am just finding a good order in which to evaluate a long sequence of multiplications. So the general problem, so this was for 3 A, B and C, but the general problem is I will be given n such matrices, right. So and we, just to make everything easier for our programming, we will as usual assume that the numbering is 0 to n minus 1, right. So we have matrix 0, matrix 1, matrix 2, each of them has a dimension, R0 times C0, R1 times, so each has a number of rows and columns. Now in order for this whole thing to work, these dimensions must match, right. So the columns of this matrix must match the rows of the next matrix, that is what this says, right. So columns of the first matrix must match the number of rows in the next matrix, otherwise you can't multiply them. So at any point, if I look at Rj, the jth matrix rows, it must be equal to the number of columns in j minus 1, right. So Rj must be equal to Cj minus 1, and since Cj minus 1 must make sense, j minus 1 should be at least 0, so j should be at least 1. So j lies between 0 and it goes up to n minus 1, so j is strictly between 0 and n. And if we do that, then we are guaranteed, because as we incrementally, so one way to evaluate a matrix is always to go left to right, right. So I can do m0 times m1. So this is the natural way if I just did not think about it, right. I will just bracket it to the left. So I will first compute m0 into m1, then I will take that and multiply it by m2. But at every point, the number of rows that I generate, the number of columns that I generate will be compatible with the next number of rows. So this matrix product will always exist. But our goal is of course to find the best way to do this. So what we want to do is find this kind of a bracketing, right. So it amounts to basically saying, how do I parenthesize the expression, how do I choose which pairs to do first, then which pair to do next, and so on, so that overall I minimize the total amount of cost I spend doing this standard matrix multiplication. So let's look at the inductive structure of this. So remember, we can only multiply 2 matrices at a time. So our final answer is a single matrix. So that single matrix must have been got by multiplying 2 matrices. But because I am multiplying this whole thing left to right, the last 2 matrices that I multiplied, so I had m0, m1 up to mn, the last matrix that I multiplied must have been of the form where I have basically taken sum up to some k minus 1 and k. So I have taken the product from k to n and I have taken the product from 0 to k minus 1. In our earlier case, for instance, we had a, b, c, right, and we have a, b, c. So in both cases, I can think of this as a trivial product where I just have 1. But if I had 3, for example, if I had 4, I had A, B, C, D, then I could, for example, do AB times CD first, or I can do ABC times D. So of course, ABC itself would require me to break it up, but at the last step, what I'm doing is I'm taking 2 sub orders, so 2 segments of this 0 to n minus 1, and I'm multiplying the result, right. So I have 0 to k minus 1 on one side, and I have k to n minus 1 on the other side for some k, right. I'm not telling you which k it is, but I know that it must be of this form. So if I now look at the dimensions of this, right, then the left matrix after all this multiplication will have the same number of rows as M0 and the same number of columns as k minus 1. So the first one will be R0 times Ck minus 1. The second product, this one, will have the same number of rows as this one, that is Rk, and the same number of columns as this one, which is Cn minus 1. And because of this compatibility thing that we had assumed, the number of rows here and the number of columns here must be the same. So Rk must be equal to Ck minus 1, otherwise we could not have done this multiplication to begin with. So that is the constraint that is assumed. So the cost we will now think of as the cost of doing it from the beginning to the end. So the cost C0 comma n minus 1 corresponds to how much time it takes or how many steps it takes to compute the entire sequence products from 0 to n minus 1, right. So what we can see from this is that this breaks up into sub costs, right. So first of all, there is this final step. The final step involves multiplying these 2 matrices, but I know the cost of that matrix because I've told you what the costs are, right. So I've told you the rows and the columns in these 2 matrices. So it is the number of rows in the first matrix times the number of columns in the first matrix, which is also the number of rows in the second matrix, times the number of columns in the second matrix. So it's R0 times Rk times Cn minus 1. So this is the specific cost I get for the final multiplication. And then inductively I have incurred a cost in getting to this stage at all. So I must have done something from 0 to k minus 1 to get this matrix. And similarly, I must have done something from k to n minus 1 to get this matrix. Right? So these were the inductive problems I solved. So my total cost is going to be the sum of these 3 values. It's going to be the cost of building up the first factor, the left factor, the cost of building up the second factor, plus the cost of combining these 2 factors in a final multiplication. So this is the only one that I know explicitly. The other 2 I have to inductively compute. So of course the choice of k is what determines how efficient it's going to be. So which k should we choose? Point here is we don't know which k to choose, right. So this is like even in an edit distance problem, we don't know whether we want to substitute, delete or insert. So similarly here we don't know whether we should choose k equal to 0, k equal to 1, we can choose any k. So what we have to do is basically evaluate the possibilities for all choices of k and then take the minimum, because remember again we want the minimum cost for this matrix multiplication. So what do the sub-problems look like? So if you look at this case, the sub-problem consisted of starting from 0 and going to some intermediate point, and then starting from that intermediate point plus 1 and going to the end. But in turn, these problems will again decompose. So if I take, for instance, this first part, right, if I just take the first factor, then this in turn will have decomposed into something in between, right. So there will be some j in between, such that it's 0 to j minus 1 and j to k minus 1. So I could have a segment which I have to multiply in order to determine its cost, which starts from somewhere in the middle and goes to somewhere in the middle. So in general the problem starts from some j and goes to some k, right. So we will look at a generic subproblem of the form mj plus 1 up to mk. And for that we will write the cost as Cjk, right. So Cjk is the cost of multiplying mj plus 1 to mk, and this will now be, by our calculation, we said we don't know how to split it, but we have to split it at some L between j and k, right. So we find some L which is between j and k, and we look at the cost of doing j to L minus 1 and the cost of doing from L to k, and plus the cost of multiplying Cj times RL times Ck, right. So remember that RL is equal to CL minus 1. The number of columns in the last element in the first factor is equal to the number of rows in the first element in the second factor, right. So this times this is the final multiplication, and then these 2 are our inductive things, right. So possibly I should have written the round bracket here, so you can just ignore it for now, I will fix it, right. So this is the inductive definition of our cost. Now what is the base case? Well, the base case is when I actually have to just have, so remember that one of the cases that we had, for instance, was A times B times C. So if in this case right? What we had was we are multiplying a single matrix by a product of a chain of matrices. So the base case is when the sequence consists of only one matrix. But when the sequence consists of only one matrix, there is no multiplication to be done, right? So if I look at j comma j as my interval, then the cost is actually 0. So I can use that as the base case for this definition. So we have these sub problems, as we said, which start from I and go up to j, and I and j can be between 0 and n minus 1, right? So we will naturally have a square matrix representing all the possible costs that we need to compute using our inductive definition. But there is another constraint on these costs, which is that I know that the second index j cannot be smaller than the first index, right? So I comma I is the smallest I can start with. I can't do I comma I minus 1. It doesn't make sense to start from a position and multiply by a matrix before it, because I always do matrix multiplication left to right. So matrix multiplication is associative, but it is not commutative, right? Commutative means that AB is equal to BA, right? So for matrix multiplication, this is not the case. I cannot. First of all, it may not be possible, because if I look at AB, the compatibility of the column and the row will be there, and for BA it may not be there. But supposing they are square matrices, right? So supposing this is some n times n and this is also n times n, so I can actually multiply both AB and BA. In general, the product AB is not going to be equal to the product BA. So I am not allowed to flip the order. I have to go from left to right. So that means in any sequence I must go from I and stop at a position to the right. So J is always bigger than I. So what this means is that in this matrix, right, I must only look at cases where j is bigger than I. So here, for instance, if I look at this entry, right, so let's look at this entry. Let's assume that this is 1 and this is 1, right. So if I look at this entry, then this corresponds to I equal to 0, I equal to 1. So this is I and this is j. So row 0 and column 1, row 1 and column 0, and this is not allowed. So everything in this blue zone, right, corresponds to j, which is smaller than I. So the first entry of interest is where I is actually equal to j, and after that I is smaller than j, but below that is not allowed. So I only have to compute values above this so-called main diagonals, right. So this is the diagonal of the matrix and this is the main diagonal. So we only need to compute values on the main diagonal and above. The other thing is that our matrix product says that Cij depends on this Ci to k minus 1 and Ck to j. Remember, I have I up to j and I am splitting it at some k minus 1. So there is some value of k between I and j where it splits. And if I try to look at what that means, it means that I am looking for a value in the same row to the left and in the same column but below, right. So concretely, if I take this as I and j, this yellow square as ij, so I have I here and I have j here. So if I take this as my concrete square, then the first value is to take k is equal to I itself, right. So if I take k is equal to I plus 1, then k minus 1 is equal to I, right. So the first factor goes from I to I. So that's this one. This is the cost Cii, right. And here now this is the factor I plus 1 j, right. So I have to look at this cost, the cost of this plus the cost of this plus the product that arises by taking those as my intermediate things. That is one factor. The other one is I move it by 1. So I now allow a chain of I plus 1, and here I start at I plus 2 onward. So I get this and this, right. And the third one is this one. So in this particular case, if this is my position for I and j, then I have this pair, then this pair, and then this pair, right. So I have to look at all of these. So what this means is that therefore I need to know the values on my left and below, and this you can see is proportional to the position where I am, right. So unlike our LCS or LCW matrix, where I always looked at only the 3 entries, so wherever I was in the matrix in LCS or LCW or in edit distance, I only looked at my immediate neighborhood, right. I only looked at the right to the bottom and diagonally to the bottom and right. So it didn't matter where I was. Whereas here, if I am here, for instance, I will need all these values, right. So depending on what the position is, I might need order n values to compute. So this is the difference between this computation and the earlier computations, which is that the number of sub problems that I have to consider to evaluate a given position is not constant, right. It's not fixed. It depends on where I am, and in general it could be as bad as order n. So what are the base cases? We saw that the base case is when I is equal to I, right, or I is equal to j rather. So we said that when I'm only looking at a singleton matrix, there is no cost involved. So I can fill up this base case to begin with. Now that I filled up the base case, then what can I fill? Well, if I take a value here, for instance, I can't fill it because I have to look here and here. I can't even fill a value here, right? I can fill this value, yes, but I can't fill this value even if I filled this value, because if I've filled this value and I try to fill up this value, I still have a missing value here. So I cannot go row by row and I cannot go column by column. I have to look at it diagonally, right? So what I have to do is I have to then, after filling this, I have to fill the next, because for the diagonal entries, the next diagonal above the main diagonal, for every position I do have something to its left and below, right? So this I have its left and below. So for every one of these, I know both the items in the same row and the same column to the left and below. So I can fill up this. Then I can fill up the next diagonal. So if I take a typical entry in the next diagonal, again I have all the things to its left and below, right? So I can fill up these entries diagonal by diagonal. And in each case, when I come to an entry on that diagonal, everything that is to the left or below has already been filled by an earlier diagonal. So that's what I need for dynamic programming to work, that when I need a value, I need a subproblem's answer, I am not going to re-evaluate it using recursion or the inductive definition. I am going to assume it's already been calculated. So by doing it diagonal by diagonal, I make sure that whenever I reach a problem, all the subproblems have already been calculated. So this now becomes a little more tricky to program, as we will see. So in this way you fill up this thing, right, and eventually what are we going to get? We are going to say that this is the value that we want, right? This is the cost that we incur when we break up the entire segment from 0, so this is I is equal to 0 to j is equal to n minus 1. So if I take the entire sequence or the chain from m0 to n minus 1, that is the cost 0 to n minus 1, right? How much cost does it take for me to do that? So this top right corner value is going to be the answer, just like for this edit distance, the top left corner value, the 0, 0 value is the one I wanted. So as I said, this is a little more tedious to program, so let's just go through the code a little bit more carefully. So first of all, here we need some non-trivial input. Earlier we had 2 strings, for example, so I could just pass it. Now here I need this sequence of rows and columns. So let's assume that I get as input a matrix of length n where each entry is of the form RICI, right? So I have R0, C0 and then R1, C1. So these are the dimensions of the n matrices up to Rn minus 1, Cn minus 1, right? So this is my input. I get a dimension matrix consisting of pairs of entries RICI. So if I am using NumPy, then I can extract the number of entries by using the shape function, right? So the shape function will give me a, for a one-dimensional matrix, it will give me something of the form n comma 0 or n comma blank like this. So I need to use this 0 thing to get out n. So basically I can extract the number of entries, and then using that I can set up as usual an empty matrix to store my answer. So C is my cost matrix, so I set up an n by n cost matrix with value 0. The first thing I do is of course it's already 0, but just to emphasize, I set the base case, right? So for all entries from 0 to n minus 1, I set Cii equal to 0. So strictly this is not necessary because I already have the zeros here, but this is just to emphasize that the base case is being handled. Okay, now I have to do this diagonal. So this diagonal is what I wanted to mention to you carefully. So let us look at a specific example, right? So let's say that we have, say, a 5 by 5 matrix, right? So these are now 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So I've already done this. So this is done, right? So this is my main diagonal, which is I is equal to j. So now I need to enumerate these pairs. So what is the property that all these pairs share? Well, you can look at this. Here it is 0, 1. This is the first one, right? The second one is 1, 2. Third one is 2, 3. And the fourth one is 3, 4. So the property that all share is that j minus I is equal to 1. Now if I go to this one, for instance, right, then it will be 0, 2, 1, 3 and 2, 4. So now the difference is going to be j minus I is equal to 2. So the difference will go from 0 on the main diagonal. In the main diagonal, the difference between j and I is 0 because I is equal to j. Next one, it is j is equal to I plus 1. Next one, j is equal to I plus 2. And finally, when we come here, right? When I is 0, j is n minus 1. So, the difference goes from 0 to n minus 1 as I go diagonal by diagonal, but the 0 case has already been handled, right? So, I will take my differences to run from 1 to n minus 1. Now, if I run my difference from 1 to n minus 1, then I have to figure out what is my range for the rows. So, the rows always start at 0, okay, but you can calculate that the last row that I get, if the difference is 0, then I go up to n minus 1. If the difference is 1, then I go to n minus 2 and so on. So, I go to n minus the difference, right. So, this is telling me how to generate the I part of this. So, I need to generate the I part. Once I generate the I part, the j is easy, right? The j is just I plus the difference because j minus I is constant. So, I am generating all the ij pairs systematically by fixing the difference, and then for each value of the difference I am fixing all the valid i's, and for each I get the j by just adding the difference. So, that is what this part is doing, right. So, it is saying that let the difference run from 1 to n minus 1, let I run from 0 to n minus the difference, n minus 1 minus the difference actually, right. So, and then let j be equal to I, and then I have to take this minimum, right, of those quantities. So, one way to take the minimum is to initialize the value to something large and then take the minimum, but since I do not want to speculate as to what the large value is, I first initialize it to concretely the first value. I say the first value is going to be, if I split I as I plus 1 up to j, then the smallest value is when I split it this way, right. So, I take Ci, the cost of I to I, the cost of I plus 1 to j, both of these should be known because they are already below and to my left, right. And then I take the concrete cost of this multiplication, the rows of I plus 1 and the columns of j, right. So, this is the concrete cost. So, this is the first term in my minimum sequence. So, I use that to initialize my cost. The cost of ij is at least this much, right. And then I range over all the possible i's and I keep taking the minimum of the current cost and the cost I get for the new value of k. So, the rest of it is straightforward. So, this part is kind of straightforward. This part is a little bit non-trivial because for minimum it is not like maximum. For maximum you could always take a negative number or 0 because you know that you are not going to generate negative numbers in this kind of a cost calculation. But for minimum you have to take a large number. So, either you can postulate a large number which is more, so one, for example, value that you can take for the large number is the product of all the rows and the columns. You know that it is m into n into p. So, if I just take the product of all the ri's and the ci's, certainly that is an upper bound on any cost. But it is simpler to actually take concretely, and every time you take the minimum, take the first value. If you are taking the minimum of any list, you can take the first value as your starting value for the minimum and then take the minimum with respect to that, right. So, that always works. So, that is what we are doing here. But the main new thing is this part, how to enumerate the diagonals. So, in this case the diagonals are the main diagonals, so the difference is constant. So, you just have to take the constant difference and then enumerate the correct values of I, and for each j you just get it by taking I plus difference. So, this works, and you will actually get that answer. For example, for the example we looked at the beginning, that 1 into 100 and 100 into 1, you will get the answer 200. So, what is the cost of this whole thing? Well, obviously we are filling up a table of size n squared, so that is what the amount of work we have to do. But now remember that unlike in edit distance or in any of the earlier problems we looked at, each entry is not a constant amount of work, right. Each entry could involve looking at a number of, so we have this for loop inside for filling up an entry, which we did not have earlier. So, each entry in the worst case takes order n work. So, this whole thing now is actually order n cubed. So, that is why this is an interesting problem to look at, because unlike the earlier cases where the dependency is very local and it only depends on your immediate neighbors compared to what value you are trying to put into the table, here the dependency actually requires you to evaluate linear number of combinations and then take the minimum. Okay. So, therefore, you get an extra factor in your complexity which comes from the cost of filling the entries in your table.